Welcome to Unit G482, Module 1, Electric Current. This is the first lesson in the series and we're going to be learning about current and charge. The first thing you need to be able to do by the end of this lesson is to define electric current. You need to be able to define the Coulomb and you need to be able to calculate current and charge using the current equation. You also need to be able to state Kirchoff's first law and apply it, and you need to be able to explain which conservation law Kirchoff's first law relates to.
First of all, let's look at the structure of metals and what makes them such good conductors of electricity. Metals are made up of positively charged ions in a regular arrangement known as a lattice. They've become positively charged by giving up one or more negatively charged particles known as electrons into a sea of delocalized electrons. These electrons are free to move around randomly in every direction. It is the ability of these electrons to move around that means that metals are such good conductors of electricity, as they can transfer the electrical energy from one place to another. Each electron is 1.6 times 10 to the minus 19 coulombs of charge. Now, charge is a quantity that you need to know about for your exam. It has a symbol of Q and it has a unit, i.e. is measured in coulombs. The unit symbol is C.
As I just said, the delocalized electrons move randomly in every direction around the positive lattice ions. This is not very useful because the good thing about electricity is that it transfers energy from one place to another. So to get that energy flowing from one place to another, we need the electrons to flow in one overall or one net direction. So let's look at how we can get them moving in one overall direction. Let's consider the metal we were looking at in the last slide, but now don't look so closely, but instead zoom out and draw it as a wire like this. Like we said, the negative electrons are moving around randomly in every direction. There is not one overall direction in which they're flowing. So let's attach it to a cell, in more specifically the positive terminal of a cell, and the electrons might be attracted towards that positive terminal, so we might get the flow in one overall direction. Unfortunately, the electrons won't start to flow towards it because they have nowhere to go and they have nowhere to come from. So what we need to do is to attach the other end of the wire to the negative terminal of the cell, and what we have now is a complete circuit where the electrons will be repelled from the negative terminal and attracted towards the positive terminal. What the cell does is it provides energy to the electrons to enable them to flow. And so what we say is there's actually a potential difference across the cell. Don't worry about potential difference for now, though, as it's a quantity we're going to come to in a later lesson. So we have negative charge flowing in this direction around the circuit. Current can be described as the amount of electricity that's flowing past a point every second. Okay, so we've got negative charge flowing down this wire, and the amount of charge that flows past one point in that wire every second is known as the current. Or a more specialist or technical term for current is the rate of flow of charge, and you need to learn this definition for your exams. Rate is basically getting at the idea of it. The quicker the current is flowing down this wire, the bigger the current is. So high rate of flow of charge, i.e. it's flowing down quickly, that would be a high current. Or if lots of charge flows past that point every second, then again that will be a high current. Right, so current is just a quantity you need to be aware of for your exam, and the symbol for current is I, and the unit, i.e. what we measure current in, is amps, and the unit symbol is capital A. So traditionally they thought current was the flow of positive charge. So they thought something was coming out of the positive terminal and into the negative terminal in that direction. So this is what we call conventional current, and it flows from the positive to the negative terminal. In fact, this is still how we define the direction of current, and we define the direction of current as the direction of net overall flow of positive charge. Okay. However, with the discovery of the electron, we realized that current is actually the flow of negative charge out of the negative terminal and into the positive terminal. And this is what current actually is. Electron flow from the negative to the positive terminal. This doesn't change anything though. Even though we've got electrons, i.e. negative charge, flowing in that direction, that is the same as saying we've got positive charge flowing in that direction. And that is how we define the direction of our current, remember. The net overall direction of flow of positive charge. And we'll have a look at that in a bit more detail in a later slide. So we've already looked at how current can flow through a metal solid, but let's now see how we can make current flow through a liquid. Liquids that allow currents to flow through them are known as electrolytes, and electrolytes are quite simply ionic compounds dissolved into water to form a solution. When the ionic compounds dissolve, the positively charged ions separate themselves from the negatively charged ions and go into the solution. And when these particles go into the solution, they are free to move around. So you should already see how electrolytes lend themselves well to having current flowing through them. Think back to the metal, and it was the ability of the negatively charged electrons. It's their ability to move that meant metals could conduct electricity well. And here we have, in the electrolyte, we have positively charged particles that are free to move and negatively charged particles that are free to move. So let's look at how we can get a current flowing through this electrolyte. Remember how we said we defined the direction of current to be the direction of net overall positive flow of positive charge. So if we put a negatively charged cathode into the water and a positively charged anode, and they are charged by connecting them up to some external electrical circuit, then what will happen is the negatively charged ions will flow towards the positive anode, and the positive charged ions will flow towards the negative cathode. And so what we end up having is a net overall flow of positive charge towards the cathode. And there we have it, our current. Let's have a look now at how the current in an electrolyte compares to the current in a metal solid. Think back to the metal solid, and the way a current was flowing in a metal solid is the negatively charged electrons moved in one direction, say towards the right. However, the positive ions here, remember, stay stationary. So having electrons flowing towards the right, for example, is the same as saying we have a overall net flow of positive charge to the left, and that's how we define the direction of our current. However, in an electrolyte, both the negatively charged particles and the positively charged particles are free to move. So in this case, the electrons went to the right, the negatively charged ions went to the right, and the positively charged ions went to the left. And so again, this is the same as saying we have a net overall flow of positive charge towards the left, and that's our direction of current. So in this one, both positive and negative are free to move, whereas here the positive are stationary, and it's just the negative electrons flowing in one direction that give us the current in the other direction. As a side note that is still important, you need to understand, if we put both this positively charged ion and negative charged ion back together, so we bonded them back together and then made that combination of positive and negative particles bonded together move, say, towards the left. If they're moving together, both the positive and negative particles move together in that direction, that's the same as saying no charge moves in that direction, because they cancel each other out. So we have no net overall flow of positive charge in any direction, so in that case we wouldn't have a current flowing. Whereas in both these situations, both the metal and the electrolyte, we have a net overall flow of positive charge in a certain direction, so we have a current flowing.
Now, remember that electric current is the rate of flow of electric charge. Like I said, this is how much charge flows past a point in 1 second, and it is from this definition that the equation follows. To calculate the current I that is flowing, you need to know how much charge is flowing past a point and how long it takes to flow past that point. If you divide this charge by this time, you can calculate the current. Now we want the current to be measured in amps and the charge to be measured in coulombs and the time to be measured in seconds. If we rearrange this equation, we end up with charge is equal to current times time. This leads us to our definition of the Coulomb. If a current of 1 amp flows for 1 second, the amount of charge that flows is equal to 1 Coulomb. And so this is our definition. 1 Coulomb is the amount of charge that flows when a current of 1 amp flows for 1 second. And this is another definition you need to know for your exams.
Right, let's see if we can use this equation in a question now. If you want to pause the video now and give the question a go yourself first, then please do. So the question says, what is the current that is flowing if 5 coulombs of charge flows past a point in 2 minutes? First of all, write down the quantities that we are given, which is charge is equal to 5 coulombs and time is equal to 2 minutes. Now we want charge in coulombs, so that's fine, and we want time in seconds. So we need to convert this, so it's 120 seconds. Write down the equation we want to use, which is I is equal to Q divided by T. Then we just put in our numbers. 5 divided by 120, and because this is in coulombs, the charge is in coulombs and the time is in seconds, we've got coulombs per second, so that gives us our answer out in amps, and it comes out as 0.04 amps. Right, let's look at a slightly more difficult question now that asks us to calculate something different and also means we have to convert units to the units we want. Again, pause the video now if you want to give it a go yourself. So this question says how many electrons flow through a light bulb if a current of 5 milliamps flows for 20 minutes. So we know what the current is, and that is 5 milliamps. We don't want that in milliamps, we want that in amps, so we've got to convert the units first. So it's 1,000 milliamps in an amp, so either divide 5 by 1,000 or write down 5 times 10 to the minus 3 amps. And we know that the time is equal to 20 minutes. Again, we want that in seconds, we've got to convert units again. So it's 20 times 60, 1,200 seconds. So we know current and we know time, which means that we can work out the charge that flows. But we want to find out the number of electrons that flow. But if we work out the amount of charge that flows, because we know the charge on each electron, we can then work out how many electrons that charge represents. So first of all, let's work out the charge. We need to rearrange our current equation. So we have Q as the subject, so it's charge is equal to current times time. So we have 5 times 10 to the minus 3 multiplied by 1,200, which tells us that 6 coulombs of charge flows in that 20 minutes. Now remember, we know the charge on an electron is equal to 1.6 times 10 to the minus 19 coulombs. So each electron has that amount of charge. We know we've got 6 coulombs of charge though. So if we divide 6 coulombs of charge by the charge on one electron, that will give us the number of electrons. So that will be equal to 6 coulombs divided by 1.6 times 10 to the minus 19 coulombs per electron. And that tells us that we have 3.75 times 10 to the 19 electrons that flow in that 20 minutes. Okay, so let's look at how current varies as it flows around the wire in a circuit. Remember that we learned that current is actually electron flow, so the flow of negative charge out of a negative terminal into the positive terminal. However, by convention, we draw our current arrows in the direction of conventional current, i.e. the flow of charge out of the positive terminal. So to help us in this way, we're just going to consider charge flowing out of the positive terminal, even though we actually know charge is flowing out of the negative terminal. The more charge that flows past a point in a wire every second, the higher we say the current is. And if we've got one loop of wire like this, then it follows that the charge at every point along the circuit will be travelling at more or less, will be travelling at the same average speed. So that means if we've got a loop of wire like this without any junction in it, then the current at every place will be the same. So if we consider the current I1 here, I2 here, and I3, it follows that I1 equals I2 equals I3. Even if we put a resistor in that tries to decrease the current, this rule still follows. And this makes sense if you think about it, because charge is a fundamental quantity that needs to be conserved. So if we have a certain amount of charge coming out of the cell every second, then we need the same amount of charge going into the cell every second. And thus I1 is the same as I3. Right, so in the last slide we looked at a very simple series circuit where there were no junctions in the wire. Here now we're looking at a parallel circuit where we have what we call a junction in the wire, where the wire splits into two. Let's call this junction junction A. When a certain amount of charge flows into junction A every second, it has the option of either going towards R1 or R2. Some of it will go towards R1 every second, and some of the charge will go down towards R2 every second. Now remember, charge is a fundamental quantity that needs to be conserved, so the total amount of charge going into the junction every second must be equal to the total amount of charge going out of the junction, either towards R1 or R2 every second. Also remember, charge per second is current, which means that the current going into the junction must be equal to the current coming out of the junction, either towards R1 or down towards R2. And this is Kirchoff's first law. The total current going into a junction must be equal to the total current coming out of the junction. And this follows from the conservation of charge, and is another definition you need to know. So let's call this current IT, and this current I1, and this current I2. It follows from Kirchoff's first law then that IT must be equal to I1 plus I2. Because as the charge per second comes in, the current, some of the current must go that way and the rest of it must go that way. Remember what we learned on the last slide as well, that along one wire, the current at every point must be the same. So it follows that the current here must also be equal to I1, as it's in the same wire. It also follows that the current here must be equal to I2, as it is in the same wire. Now, as this current comes up to here and this current comes into this junction, these two currents join together to make a new current, and let's call that I4 for now. So if we apply Kirchoff's first law at this junction now, it follows that I1 plus I2 must equal I4. Now if we look at these two equations here, the right hand side of both of them are the same, which means the left hand side must be the same. So it follows that IT equals I4. So let's have a look at what's actually happening in the circuit to see why IT must equal I4. As we learned before, the current in one wire must be the same at every point, and this can be considered as one wire, so it makes sense that IT must equal I4. Also, the amount of charge coming out of the cell every second must be equal to the amount of charge coming into the cell every second, due to the conservation of charge. So that's the same as saying the current coming out of the cell must be equal to the current going in the cell. Again, IT equals I4.